All right. On our last topic, you were introduced to the concept of a limit, right? So what did we say a limit was? Okay, as f of x becomes arbitrarily close to a specific y value at the same time that x is approaching a specific value, if it equals to the same thing from the left and the right, then we can call it a limit, right? Okay. Now, we're going to discuss something known as continuity at a point. Now, the first word is continuity. Continuity is not anything that's new to you. You with me? Can you describe to me in your own words what continuity means? Yes. Okay, very good. Got ahead of me, but totally acceptable, right? So using calculus, you're saying we're going to use limits. If we have a limit, and then you're saying if it's equal to what again? I'm sorry? That specific value, the value at that location, then we're going to call it continuity. Perfect. That's where I'm going with this. But let me ask you another question. Like, go back to pre-cal or algebra 2, right? So you were asked whether functions were continuous or not. Like, how would you describe how something continuous to someone that just doesn't know? To start out with calculus at all, just like, how do you tell something's continuous? Yes. Perfect. If you can draw without taking your pencil off the page. Cool. Now, you are in calculus. You've been through pre-cal. So you should feel very familiar with the concept of continuity and functions. Okay? I'm not going to discuss today continuity over an interval. You with me? I'm discussing continuity at specific points. Okay? Over an interval, you should already kind of have an idea of how to do that. For example, if I ask you, can you describe the continuity of polynomials, you should say what? There are continuous everywhere because polynomials have absolutely no breaks. Are you guys with me? Like if I ask you to describe the continuity of rational functions, what would you say? They're not always continuous. Why? Because you can have what? Wholes or asymptotes. So there is expectation of knowledge from the past. Are you guys with me? But right now I'm going to focus at a point, which is exactly the definition that you gave me. Okay. For me to make a decision about continuity at a specific point, a limit has to exist. Cool. So we'll start out with that. So the limit has to exist. So number one is the limit as x approaches a specific value of a function must exist. Like that's not negotiable. Cool. The second thing is you said that there has to be a point. Cool. So what I'm going to say is f of c must exist. Now, if you recall, for the previous topic, I did ask you to find limits, but I also asked you to find like f of something, right? So in order for me to claim continuity, so far, the limit has to exist and the point has to exist. But in order for me to say that it is continuous, I have to make a connection between those two things. What would that connection be? That they're exactly the same. So I would have to say that the limit as x approaches c of that function is, in fact, the same value as f of c. That's the only way I can claim using calculus that we are continuous at a specific point. And that is the expectation from now on about continuity at a point, right? You can no longer just say like it's continuous because there's not a break in the graph, for example. You with me? You have to say the limit exists, the point exists, they're equal to each other, therefore you are guaranteed continuity. Fair enough? All right, so let's do an example. How well is your graphing techniques? So we're going to put our calculators away for this one. Do you remember graphing? All right, let's try it. Let's see how well we remember. So f of x equals x squared plus 4x plus 3 divided by x squared minus 3x minus 4. I want to discuss the continuity of this function over its interval. So in other words, I want to find out if there's any discontinuities. Okay? It's a rational function, so you should be expecting, you mentioned it earlier, maybe some wholes, maybe some asymptotes. And if there are, then we're going to have some discontinuities. So I want to identify where are they happening, and then I want you to use calculus to prove that they're happening. Fair enough? So how would you attack this problem? Factor? Okay. So f of x is equal to what? x plus 1 times x plus 3 on the numerator. And then the denominator would be x plus 1, right? X minus 4. You guys agree? Okay. Why did you do that for? Okay. I have a common factor, which means it divides half, which means I have a whole. Specifically where? -1 comma something. Okay, you were taught how to find that something last year. Do you remember how to find that something? Plug it in where? The simplified version. So I need to put in a -1 right here, and I need to put a -1 back there. Why do I have to do it on the simplified version? What would happen if I put it in the original? 0 over 0. Are you guys with me? Okay, so -1 on the top gives me a 2, and then -1 on the bottom gives me a -5, so that means I have a whole exactly at -2/5. Right? Okay, what else do you think I need to find out to solve this problem? Asymptotes? Okay, what do I have asymptotes, and if so, where? Okay, so I have a vertical asymptote at x equals 4. Any other vertical asymptotes? Slants? No. Horizontals? Uh-oh. How do you find, because horizontal and slants, it's the same procedure to find them. So how do I know whether I have a horizontal or a slant? Not the coefficient, but the powers. Okay, so the powers. You can go back to the original, you can go back to the simplified version. Okay, so the original, what's the highest power? What's the highest power on the numerator? 2, the denominator 2. What happens when the powers are the same for asymptotes? Then you do have a horizontal asymptote when they're the same. Okay, and to find it, you divide the coefficients, which in this case happens to be 1. Okay, what happens when the degree on the bottom is bigger than the top? You have a horizontal at y equals 0. What happens when it's bigger on the top? You have a slant, not a horizontal. And how do you find it? Using division. If you don't remember those things, make sure that you get help as necessary. Okay, so for right now, that's the information that I have. What do you want to do with it? Graph it? Or, yeah? Okay, cool. Okay. Here's my x and y axis. I have a vertical asymptote at 4. Okay, 1, 2, 3, 4. And then I have a horizontal asymptote at 1. Cool. I have a whole at -1, comma, -2/5. So that, I mean, I'm going to estimate here. That would be about right here. Yes? Okay, that's all I have. What would you suggest? Plug in some numbers. I'm going to do this quickly. I can find the y-intercept very quickly. What's the y-intercept? Plug in 0. So the top would be 3, the bottom would be -4, right? So 0, comma, -3/4. So that means the y-intercept is somewhere like right here. And I think I have enough information to know what's going on, because I know that these two have to connect, and I know this asymptote is going to pull me in this direction, and then I know this asymptote is going to pull me in this direction. Fair enough? All right, how do I figure out what's going on the right side of 4? You're actually going to have to figure out some number, right? So are you okay if I put in number 5 into the function? Like, okay, so I'm not going to go to the top. I'm going to go to the simplified version. So 5 plus 3 is 8. 5 minus 4 is, so when I plug in 5, I get 8. So that's going to be somewhere up here, right? So 1, 2, 3, 4, 5, like way up here. So that guarantees that this graph is going to look something like that-ish, right? All I needed is a sketch. Cool. Now that you have a visual, is this continuous? No. Do you have discontinuities? We do. All right. Upon our return from lunch, I will continue this video. Okay, so right before we left off, here's the graph that we came up with, and we all agree that there was 2 discontinuities, right? Okay, so number 1 is you need to know the names of the discontinuities, so we'll discuss that, and then how we're going to use calculus for you to prove the discontinuity, okay? All right, so the first discontinuity, what x value would you say it's happening at? Which one, I'm sorry? -1? Okay, so this one right here, we have a discontinuity there. Cool. Does anyone by any chance know the type of discontinuity that is? It's called a removable discontinuity. So it's a removable discontinuity, also known as a hole for you. Some of you guys in pre-calc. Remember that? Okay. So let's use calculus to prove that it's not continuous. Okay. So how would you use calculus to prove it? Okay. I gotta use the limit, right? So I gotta say the limit as x approaches what? -1 of f of x. In this case, what is that limit equal to? It's -2/5. So the fact that we found the hole really helped us out. Cool? All right. What else do I need to do in order to prove the discontinuity? F. So I need to figure out what f of -1 is. Okay, what is f of -1? Not defined, right? So undefined. So then, in this class, you're going to have to write statements to back yourself up. So you're going to justify why you are going to say that it's not continuous. Okay, so what statement could you make? Yes? Okay. I like what you said, but I would, instead of using C, I want you to use the numbers that you are provided. So we're going to say the limit as x approaches -1 of f of x doesn't equal what? F of -1. Okay. Therefore what? Therefore, by the way, that I don't know if you know that 3 dots in a triangle means therefore. F of x is not continuous at x equals -1. Cool? For grading purposes, I'm just kind of communicating this to you. Like, if you only give me this information right here, and then that's it, that's all that's on your paper, you missed this question. You didn't answer the question. You understand what I'm saying? That's just your work. You never made a conclusion about your work. The actual answer should be the statement below. Fair enough? Okay. Other types of discontinuity that you see here on this graph? We have a vertical asymptote. Okay? So vertical asymptote has a name for discontinuity, and it is called a non-removable discontinuity. So we have a vertical asymptote here, and that is known as a non-removable discontinuity. Cool? And once again, we're going to use calculus to prove it. So, kind of running out of space, I'm just going to go up here. So tell me, using calculus, what do I need to do for that specific location? Find the limit. Okay. The limit as x approaches what? 4 of f of x. You said does not exist. Why? Why does it not exist? What do they approach? Like, if I ask you for the left-sided, what is the left-sided approach? Negative infinity. Does anyone not understand why the left-sided is going to negative infinity? And the right-sided? Positive infinity. So they're not approaching the same value, therefore it does not exist. So, since I'm proving continuity, do I actually have to go any further? So then how can I then use the given information to then come up with a statement? Then it cannot. So basically, my question is, does the limit have to exist in order for you to be continuous? Basically, yes. So the fact that it already doesn't exist, you can stop. You don't have to go any. You can go further if you want to. It's not going to take as long to answer the second part, right? But the fact that we don't have a limit is enough for me to say that I'm not continuous. Okay. So therefore, since limit f of x is not continuous at x equals 4. Cool? All right, so let me ask you one more question before we move on. You just told me that in order for it to be continuous, the limit has to exist, right? Right? What about the opposite or the converse? If the limit exists, does that guarantee continuity? No. All right, don't mistake those two things. Continuity requires that the limit exists, but the fact that you have a limit does not guarantee continuity. Fair enough? Cool? All right. There's a third type of discontinuity that we need to discuss. I just was not able to do it on the same problem, so we're going to do one more. And I'm going to use something known as a piecewise function for this. Do you remember those? All right, beautiful. So I'm going to try to keep it simple. So let's say I call g of x equal to the piecewise function where x squared is defined when x values are less than 2, and 2x minus 1 is defined when x values are greater than or equal to 2. And I'm interested on figuring out the limit as x approaches 2 from the left, the limit as x approaches 2 from the right, the limit as x approaches 2 of f of x, I'm sorry, g of x, my mistake. And lastly, what is g of 2? And then use that information to make a statement whether this is continuous or not. Fair enough? All right, so once again, for those of you guys that have taken AB, you probably know how to solve this algebraically. I'm not interested with the algebra today. I'm interested on solving them with techniques that you've learned thus far, which is graphing or numbers. So what do you want to do for this specific problem? Graph? Okay, that shouldn't take us too long. So here is my x and y axis. Okay, x squared is a parent function. That's pretty simple. I know that I'm going through 0, 0, 1, 1, 2, 4, and so on, but I'm only supposed to graph what part of that? Things that are less than 2, right? So where would I be at 2 for that graph? 4. 1, 2, 3, 4, but I'm actually supposed to have a hole there because I'm supposed to be less than that, so then this graph is going to look something like this. Fair enough? Because it's less than 2, right? And then for the other side, how would you come up with it? I mean, it's a line. It should be relatively simple to graph. We know that it has a y-intercept of -1 and a slope of 2, but I shouldn't really graph the y-intercept because it's not part of the domain that I utilize. So to make this quick, I'm just going to plug in 2, which gives you what? 3. So at 2, I should be at 3, which should give me an actual point there, right? And then use the slope, right? So rise over run. So it's just going to go up 2 and continue in that direction. So here's what my graph looks like. Cool? Now that you have a visual representation, you should be able to answer the questions on the left side. So the limit from the left gives you what? 4. The limit from the right? 3, which means the overall limit doesn't exist. And does g of 2 exist, actually? It does. It's 3, right? Using the information, you can deduce that what is happening at 2? It's not continuous, right? But let's talk about it. There's a reason why I gave you this example. We need to be able to identify this type of discontinuity. Do you know the name of it? Let's call it jump discontinuity. Cool? So this is called a jump discontinuity. Also, some people call it also non-removable. So non-removable has 2 types of discontinuity if you want to think about it, which are vertical asymptotes and jump discontinuities. Fair enough? So g of x is not continuous at x equals 2 since limit as x approaches 3 of g of x doesn't exist, right? Questions? Do you feel like you understand the idea of continuity as far as calculus goes? Yes? All right, beautiful.